Stop reading your textbook. No, seriously, close it right now. If you're just sitting there passively highlighting pages and hoping it sticks, you are literally wasting your time. Welcome to the explainer that's going to flick your entire revision strategy upside down.
So here's the painful reality, guys. You can endlessly reread those forces chapters until you've got them memorized word for word, and you'll still walk into the exam and lose vital method marks. Why? Because reading isn't revising, strategy is. And today, we're fixing your strategy for good.
Think about the exact contents page from your Cambridge coursebook. Now everyone just stares at Chapter 4 on turning effects and Chapter 5 on forces and matter. You know, they memorize what a moment is or what Hooke's law says and they think, awesome, I'm ready. But memorizing those headings, it absolutely will not save you if you don't actually understand the strict expectations of the examiner.
Okay. Let's dive into this. These right here are what I call the mark droppers. They are the exact fatal errors students make every single year when answering questions on Hooke's law and moments. We're talking about missing units, early rounding in your calculations, vague explanations, mixing up variables, swapping your graph axes, and oh man, offering incredibly weak practical improvements.
Now, I want you to pause for a second, think about it, and predict right now, which of these mistakes do you think is the most devastating for your final grade boundary? Like, which one actually costs you the most method marks in a Cambridge 0625 exam? You got an answer in your head? Okay, good. Keep it right there.
So the reason ordinary revision completely fails is because there's this massive gap between simply knowing the textbook facts and actually meeting the examiner's expectations. You might know the physics inside out, but you aren't speaking the examiner's language. To bridge this gap, you don't need to read more pages. You need a specific examiner-approved framework for how you construct your answers.
And listen closely to this, because in a moment, I'll show you the examiner clue that changes the Hooke's law answer completely. But first, you really need the framework that makes that clue absolutely obvious, because if you miss this framework, you're definitely going to miss the marks.
Let's jump into Section 1, the four-step framework, concept to examine our wording. This is your definitive strategy to stop bleeding those precious method marks.
Here are the 4 steps you need for literally every past paper you tackle. Step 1, identify the core concept that's hidden in the question. Step 2, extract the exact evidence or data they give you. Step 3, apply scientific reasoning to perfectly connect that concept and the data. And finally, Step 4, translate the whole shebang into precise examiner wording. So let's see how this builds a completely bulletproof answer.
Moving on to Section 2, applying the framework, specifically to Hooke's law and center of gravity.
Right, let's quickly anchor the core concept here. The spring constant is defined as the force per unit extension, but crucially, and you can't forget this part, only up to the limit of proportionality. That definition right there is your starting point. But simply writing that down just isn't enough when you're faced with a data table. Let's look at how students completely ruin their calculations when the exam suddenly throws actual numbers at them.
All right, Section 3, the trial, spot the error. I'm going to challenge you to actively engage right now. Let's see what you've got. So consider a mock set of student data for a Hooke's law experiment. We've got force on the left column and extension in the right. The values go from 2.0 to 8.0 for force, and they go from 4.5 up to 25.2 for extension. Take a really good look. I want you to spot the critical errors in the table design and the data itself. What is fundamentally wrong here?
Now, what's really interesting about this is the mistakes are hiding in plain sight. First off, check the headers. Force and extension. Yeah, but measured in what? Newtons? Centimeters? Millimeters? Missing units in your tables will literally cost you marks immediately. Second, look at that final data point. A force of 8.0 yielding a massive jump to 25.2, that is an unchecked anomaly. Ignoring anomalies like that leads to conclusions that the examiner will instantly and harshly penalize.
And this same exact lack of precision totally ruins answers about center of gravity in moments too. A really flawed student instinct is to just write, the object balances because weights are equal. Honestly, that gets you almost nothing. Instead, you need that elite top band wording, which is clockwise moment equals anti-clockwise moment about the pivot. Notice the precision there? It names the exact principle, the principle of moments, and it specifically references the pivot. That is exactly how you execute Step 4 of our framework.
And we really have to escalate the difficulty here, because honestly, one mistake almost always leads to another. These are what we call cascading errors.
When you calculate moments or spring constants, rounding too early in your intermediate steps completely destroys your final answer. Reversing your graph axes, that ruins your gradient calculation. Forcing a line of best fit through that crazy anomaly we saw earlier, absolutely fatal. And finally, stating generic, weak practical improvements when they ask how to make the experiment better.
Which brings us to Section 4, the final piece, practical investigations. Listen up, because this is where the top grades are actually decided.
So, the crucial point is this. Weak, generic practical improvements will for sure cost you your final grade. If an examiner asks how to improve the reliability of a Hooke's Law experiment and you just write something like, measure more carefully or do it again, you get 0. None. You have to be completely specific to the apparatus and the exact variables presented to you.
To actually secure the highest band, you need to run every single answer through this final examiner-style correction checklist. Number 1, check your final units. 2, avoid early rounding in multi-step calculations. 3, use precise variables. So don't just say length, say extension of the spring. And 4, ensure your conclusions actually match the data provided, anomalies included. If you run every practice paper through these 4 filters, just watch how fast your method marks instantly improve.
Okay, so you now have the framework to avoid the most common traps in forces and moments. You know exactly what the examiner wants to read, but this actually leaves a massive, glaring problem. Think about it. If you get a dataset with a wild anomaly like we saw earlier, how do you extract the exact gradient from that anomalous data to calculate the spring constant for full marks?
You absolutely cannot guess this. The practical data analysis skill required to handle anomalous gradients is highly specific, and getting it wrong cascades through the rest of your entire paper. So what you need to revise instead is in the next explainer.
That linked practical skill is the mandatory next step to stop losing marks, so you need to click on the explainer on your screen right now to master it. Are you ready to stop thinking like a student and start thinking like an examiner? Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. I will see you over in the next explainer.